In a Class 1 lever, the fulcrum lies between the load and the effort. You can check what happens by dragging the load. As the load moves further from the fulcrum, the effort required is more, whereas as the load moves closer to the fulcrum, the effort required is less. The effort arm is the distance between the fulcrum and the effort, whereas the load arm is the distance between the load and the effort. Mechanical advantage is the ratio between the effort arm and the load arm. Mechanical advantage can be thought of as the number of times your machine can multiply the force that you input. Therefore, the closer the load is to the fulcrum, the greater is the mechanical advantage. In the case of pliers, the effort arm is more than the load arm. This means that the effort that you put in with your hands at the end of the pliers gets multiplied by the ratio of the effort arm to the load arm. This magnifies the force that you put in. In the case of pliers, the effort arm is more than the load arm. This means that the effort that you put in with your hands at the end of the pliers gets multiplied by the ratio of the effort arm to the load arm. This magnifies the force that you put in. The velocity ratio is the ratio of the displacement of the effort to the displacement of the load. By dragging the load to different positions and clicking on Start, you can check the different velocity ratios. When the load is close to the fulcrum, the velocity ratio is high, and as the load is moved further away from the fulcrum, the velocity ratio is low. The efficiency of a machine is the ratio of the mechanical advantage to the velocity ratio. Efficiency of an ideal machine is 100%. However, in real life, due to frictional forces, it is always less than 100%. In a Class 2 lever, the load lies between the fulcrum and the effort. An example of a Class 2 lever is the wheelbarrow. Since the load is closer to the fulcrum than the effort is, the mechanical advantage of a Class 2 lever is always greater than 1. In the case of a nutcracker, the effort that you apply is magnified by a factor which is the ratio of the effort arm to the load arm. In a Class 3 lever, the effort lies between the fulcrum and the load. An example of the Class 3 lever is a tweezer or a tong. These are normally used to pick something that is small. Since the effort is closer to the fulcrum than the load is, the mechanical advantage of a Class 3 lever is always less than 1. The velocity of the load is, however, greater than the velocity of the effort. The inclined plane can also be considered a simple machine. Here, a load has to be lifted, but the machine makes it easier to push it along the incline. The component of the load along the incline is less than the load itself, so you have to push with a force less than the load. The gentler the incline, the less the force, but remember, the more the distance you have to push it through. The mechanical advantage of an incline is the ratio of the load to the effort, and that would always be greater than 1. In this case, the distance moved by the effort is x, and the distance moved by the load is the height h. The velocity ratio is x divided by h. So you can see that this will be greater than 1. One way to lift a load is simply to raise it, while the easier way is to push it up a ramp. In this case, you will see that by pushing it on a ramp of 30 degrees, the effort spent is half of that to raise it directly. Of course, the downside is that even though the effort is less, you have to move the effort through a longer distance. Gears are also simple machines. In this case, the driving gear is smaller than the driven gear. The velocity ratio can be expressed in many ways here. We can say it is the ratio of the rotation per second of A to the rotation per second of B, or the radius of B to the radius of A, or the number of teeth of B to the number of teeth of A. All the ratios should be identical. When the car moves up the slope, the driving gear engages with a larger gear to gain more torque. When the car requires speed, the driving gear engages with a smaller gear to gain more speed. A single fixed pulley has a fixed pulley as the name suggests, and a rope to lift a load by applying an effort on the other side. It is convenient to apply a downward effort. The tension in the string will equal to the load, and the effort will equal to the tension in the string. Therefore, the load and effort will be the same, and the mechanical advantage is 1. Since the distance moved by the load and effort is also the same, the velocity ratio is also 1. A single movable pulley has a pulley which moves with the load. Here you can see that the load is distributed over the same string, but 2 sections of the string. So each section takes half the load. A single movable pulley has a pulley which moves with the load. Here you can see that the load is distributed over the same string, but 2 sections of the string. So each section takes half the load. The effort is applied only on one side, so the effort will be half the load. By making the pulley movable, you can reduce the effort, but you will have to move it by a longer distance. Pulling an object upwards is not as convenient as pulling it downwards. You can achieve this by adding a fixed pulley to a movable pulley. The load is attached to the movable pulley, so that the load can be reduced by half. The string is then passed over a fixed pulley, so it is convenient to pull it downwards. A block and tackle system consists of 2 blocks containing pulleys connected by a rope. With 3 pulleys, the tension in each rope is 1/3 the total load. This means you apply an effort equal to 1/3 the load. With 3 pulleys, the tension in each rope is 1/3 the total load, which means you apply an effort equal to 1/3 the load. But the distance you have to apply the effort through is 3 times the distance the load is moved by. In this block and tackle system, 2 blocks hold 4 pulleys. With 4 pulleys, the tension in each rope is 1/4 the total load. This means you apply an effort equal to 1/4 the load. With 4 pulleys, the tension in each rope is 1/4 the total load, which means you apply an effort equal to 1/4 the load. But the distance you have to apply the effort through is 4 times the distance the load is moved by.